In this problem, we have a charge density that's in the shape of an ice cream cone here, and it has a radius of h and a height of h as well. It has a charge density of sigma, and our goal is to find the potential difference between a point B here at the top middle of the ice cream cone and the bottom tip of the ice cream cone here. And the way that we can begin to do this is first we'll just go ahead and start attacking the problem with finding the potential at point B, but we can use our new tool where we use infinity as a reference point to find that electric potential at some point B. And one thing that's always a good rule of thumb to use is to make sure it's actually valid for the charge density you're trying to use it for. So if we apply it to here, one way is we just kind of use a mental exercises. We just try to zoom out, imagine this being like our eyeball, and then we zoom out to infinity. Will this this charge density end up looking like a point charge? One also way you can think about is if does this have any infinite components to it? And this is definitely finite. Things that it wouldn't work is if you had an infinitely large plane where if you zoomed out, you would just continue to keep seeing more and more of the electric charge. So we're essentially good here to start working with this. And so we're going to need to identify a couple of things. First of all, this is the most general form, so for a volume charge density, so instead of a rho volume charge density, we have a sigma, which means that this d tau, which is typically a differential volume piece, this is actually a differential area piece right here. And this is going to be a lot of the setup of the problem here. And the way we're going to evaluate the electric potential at that point B is we're just going to take a circular ring here, right? We're going to start off from 0 and just take circular rings here and find the electric potential contribution from one of those point charge of the rings here. And the way we can do this is, imagine if I can just zoom out this ring real quick, and it will make a lot more sense whenever we try to define that volume charge density. Let's make it a little bit bigger, actually. So if I do that, so this is like a dramatic zoomed out version of this ring here. We know that the, let's go ahead and use orange actually, that this distance right here, that's going to be our dr, right? So what we're working with right here is we have our direction pointing outwards is dr, right? And then we also have like a d theta. Imagine this is our point of origin. This is our kind of our d theta right here. And we know if we want to find this length right here, right, we can just go ahead and use the fact that, let's see here, sine of theta, knowing that this is theta and this is theta right here. Sine of theta is equal to of course, the opposite over hypotenuse, and hypotenuse is what we're solving for, and we know the opposite is dr, and we're looking for the hypotenuse, right? And the reason why we're looking for the hypotenuse is we're going to try to find this length, though the goal is to find the surface area of this whole little ribbon, this circular charge here. But if we find this length here, we can sweep it around and multiply it by 2 pi r, and that will give us our whole charge differential area element right here. So we're just trying to find this area so we can sweep it around by 2 pi r. And so we just go ahead and solve for h here. So we'll rearrange this. So h, our hypotenuse, is dr over sine of theta. And what we have here, so this theta and this theta are the same thing. We have a really convenient relationship right here. Since this is h and this is h, we know this is an isosceles triangle, also known as, we can go ahead and mark this. This length right here is actually square root of 2 times h. And this angle right here is actually 45 degrees. So if sine of 45 degrees is 1 over square root of 2. And we can also say that h is equal to square root of 2 times dr, right? And so all we have to do is, now we have this length, is we just multiply it by 2 pi r, and that gives us our differential length. And we just take those contributions and we just sweep them all the way up. So our dA is equal to 2 pi r square root of 2 times dr. And the last thing that we need to figure out right now before we start chugging along is what this curly r is right here. And what that curly r is, it's the vector that goes from a chunk of that circular charge pointing to the place that we're evaluating the electric potential field at right here. The thing is that this always kind of changes, right? As we move up from a radius equal to 0 to a radius of equals to h, that vector is always going to be a little bit different, right? A little bit different in magnitude. But two things will always remain the same during that time. H will always move the same, and this angle will move the same no matter where we're pointing at. That triangle is always going to have a constant legs right here. And one of the tools we can use to figure out what that length is in terms of things that are constant and the things that we are integrating over, which is r, is we can use the law of cosines. The law of cosines, and again, we're trying to find out what that curly r is. And I know it's getting a little crowded here, but let me just go ahead and write it out here. So this is the curly r. We can use the law of cosines, which says it says that we can use a relationship between this known length and this known length and this angle right here to find out this unknown leg of the triangle here. So what the law of cosine says, it's the length of one of them that we do know, so h squared, plus the length of the other one that we do know, squared, but we don't quite know exactly what this is yet. So let's go ahead and define that. So this vector right here, this length, we'll go ahead and call that r prime, right? What that length is. In keeping with the other notation that we've used, which is the difference between the origin pointing to the chunk that is causing the contribution to the electric potential. And we can make another little triangle here. If we make this triangle right here, what we'll notice is this is a similar triangle to this bigger triangle overall here. So no matter where this triangle goes, we're going to know the relationship. This angle will stay the same. This length is always r, right? Because that's the variable that we're integrating over here, the variable that we're integrating over, and this angle is always theta. And since in an isosceles triangle, that means like this leg right here is also equal to r. So we have r, which means that this length, that curly r right here, is always equal to square root of 2 times r. So I'll go ahead and write that explicitly. It's equal to square root of 2 times r, right? And so that's we can use that for our law of cosines right here. So this is in keeping with our process for the law of cosines. We know that the law of cosine says it's going to be the length of one that we know plus squared, the length of the other one that we know squared. So we'll go ahead and start working on that. So this quantity right here squared is equal to 2r squared. And the last part of the law of cosines is the 2 times the product of the two legs that we know. So 2 times h times the square root of r. And then finally, hence the name law of cosines, we're going to multiply all that by the cosine of the angle, cosine of theta, which is the angle between those two. And all those kind of reside under a square root as well. So that's a law of cosines. And we have one more length that we can do. We can actually apply this, since cosine is actually going to be equal to the, I'll go ahead and write it out explicitly. Since cosine of theta is adjacent over hypotenuse, where adjacent is h, and we know the hypotenuse of the angle is always going to be 2 times the square root of h for this triangle. We can just go ahead and make that substitution. It's actually 1 over square root of 2. So when we make that substitution in for cosine, this 1 over square root of 2 will cancel out with that 1 over square root of 2. And we'll get something a lot more simple. All in living under a happy square root. All right. So we figured out everything. We figured this one out, this one out, this one out, and we can go ahead and start chugging along and start solving for the electric potential at point B. And remember, so we are just going to be varying the length of the radius and just making these little rings until we get to the very top and adding up, integrating over all the contributions to the electric potential. So it's there. Sigma 2 pi r square root of 2 dr. And now we have our curly r. Oops. All right, so we can go ahead and do some cleaning up here. Pi's cancel out. We can go ahead and move all those constants out to the front. And all that's left is this lovely integral waiting to be solved. All right, and there's a lot of different ways you can solve this integral. I'm a big believer in the calculators, and so that's what we're going to do. So if we plug this indefinite integral into a calculator, this is what you're going to get. All right. So this big chunk of stuff right here with the limits from 0 to h, that's in keeping with what we have here. And it looks pretty big, but it collapses down pretty nicely. So we'll go ahead and start inputting these limits into the different spots here. So we'll start with the limit of h. Utilizing technology. So let's go ahead and put in h. And let's see here, we don't need the limits anymore. Oops. Okay, so everywhere that there is an r, we're going to go ahead and put our limits in for h. So everywhere there's a r in here, we're going to change that to h. So let's see here. So this goes to h. This goes to h squared. And if you notice, that'll actually end up being 0. So everywhere where there's that relationship, those all end up going to 0. So just to make things easier, oops, do that. These end up going to 0. These end up going to 0. Finally, we'll look at these and put in h right here. So it's actually 2h. 2h. All right, now that's just the h limit. So now we're going to do the 0 limit. So we're going to do all that minus, right, minus, so this is all one equation, so minus the 0 limit, right? So of course these will all go to 0 again. As you can tell, this is where things start nicely collapsing down. 0, 0. Okay, now let's go ahead and start cleaning things up and start making things a little nicer. I'm just going to go ahead and just start doing some algebra, cleaning things up. Copy and paste this down to the next page. All right. Well, what do you got? So for looking at this one right here, obviously this will end up doing an h squared under the square root, so that'll just be h. 2 times h. This ends up being right here and just being h. This up here ends up being an h as well. And of course, these are all h squareds under a square root, so those just end up being h as well. H. Before moving on to the other one, we'll go ahead and clean this up. These will cancel out conveniently. Now looking at the 0 limit here, of course these all go to just straight h. H. H and H. These ones up here end up turning into negative h, negative h. Do some cleaning up on this side, so these will end up canceling out. So this whole thing will end up being a -1. These will cancel out, but what we can do here is, we'll just save for the next step. That'll be a -1, but that's a minus times minus, so that could be a positive, but we'll go ahead and collapse that down on the next term. I won't copy and paste this since we can go ahead and see that this is common to both. So we'll say this. And then give it a curly bracket, so h over 2. I'm just rewriting this one right here. So h over 2 plus h. And what we can do is take advantage of the fact that a natural log minus a natural log is equal to the natural log with a single argument of this divided by this argument. So that would be 1 plus 1 over square root of 2, 1 minus square root of 2 for that one. Let's go ahead and put that in a bracket. So this is the compressed h limit. So now we'll do the compressed 0 limit, so this bottom limit right here. Taking advantage of the same property of natural logs. Here we go. Doing some cleaning up. This is minus this one. And then this chunk is common to both. We'll go ahead and start by writing that out. So we have h for square root of 2 common to both. And we can actually just clump down all this. So this will be this natural log minus this natural log. We'll again take advantage of the fact that we can put these under the same argument whenever we have a minus. So it would just be this argument divided by this argument, which is also this argument times the inverse of this argument, which was what I'll explicitly do here. So it'll be 1 plus square root of 2, 1 minus square root of 2, times the inverse of this, which is actually the same thing. Right, so we can just do some cleaning up here. These square root of 2's will end up canceling out. And what we're left with is a sigma h in the denominator. And then a, let's see here, an 8 epsilon naught. And actually, before we even do this, so we can go ahead and, since another property of natural logs is the fact that you can do natural log of x squared is equal to 2 times natural log of x. And that's what we have here. We have an argument that's being squared here, so we can just do 2 times the natural log of our argument. Now, I think we can keep refining this further and further, but I think there gets to potentially a point of diminishing returns. So we'll just go ahead and do one last cleanup step, which is we'll just turn this argument, and we'll just try to get these square root 2's out of their respective numerators. So that would be 2 plus the square root of 2, and then 2 minus the square root of 2 here. We'll just go ahead and stop there for this one. Again, you can keep wrestling with this natural log, but I think it's a good place to stop. So that is the that's the electric potential for this point. That was a lot of work to get that one, but the next one is going to be really easy. So we'll go ahead and there. So that's v sub b in case we forgot what we're solving for, which happens sometimes. The second part of this is going to be a lot easier than the first one. The second part involves us finding the electric potential at this point A. So one of the ways that we can start off with, of course, is using our new tool, which is 1 over 4 pi epsilon naught, limit of integration, d tau. What we already found out with the first part, again, like this is sigma. This is going to be, we're going to attack it the same way, where we're going to take these little loops and integrate them up and evaluate the electric field at this point, the contribution. So like we said in the first part, this is actually a dA, where our dA is where we have, we're multiplying something in a complete circle, right? And where we're varying r, and the area of one side of that kind of like ribbon, that circle, is equal to square root of 2 times dr here. That's what we're integrating over. And this was the crux of the setup for the last one. Here, it's really easy, actually. So this was our r prime in the last one, and r prime in the last one, which we found to be square root of 2 times r, if you remember, because this is our r, and since this is a similar isosceles triangle to all this, that means this is this length is r, this length is r, this length is r, and this length is square root of 2 times r, and this length is what we're varying. That's the r prime. What's convenient about this one is that before our vector, our curly r vector that we have here was pointing up to b here, but what we have here is the magnitude is actually equal to the separation vector from the origin back to the point. So actually our curly r is equal to our r prime. So we don't have some crazy thing under a square root. We have a 2 under a square root right here. And in fact, it actually makes it all compress down pretty nicely. So let me go ahead and show you what I mean when I make our substitutions in for all these values here. So we have on the top, we have a sigma times 2 pi r square root of 2 times dr. Again, we're evaluating from r is equal to 0 all the way up to the max value, which is h up here. And then on the bottom, we just have the square root of 2 times r this time, just because of this this vector is really easy to find out. This magnitude of the vector is easy to find out. And so again, when we do some cleaning up here, you'll realize that this r actually cancels out right here, and in addition to that, our square root of 2 cancels out. So all that's left with is an integral of 1, actually, because that's all that's left in the square root. So that whole integral ends up being something really easy to solve for, and it all ends up collapsing down into just h. The integral ends up being h. So this is our electric field for this point at point A. So all right, pretty easy compared to the last work that we did, but we're not out of the woods yet. The whole point of the problem is to find the difference between the two. So we still have to do some subtraction that's left, but that's not bad. So we'll go ahead and copy and paste our value for the electric potential at point B. This is our electric potential at point B, minus our electric potential at point A, which we'll just move down here. And we'll do some algebra. So what's common to all of them is a sigma, we have an h, we definitely have an epsilon naught, and we have a 2. All right. And so all that's going to be multiplied by, let's go ahead and put a bracket, make things a little cleaner. So we have a natural log of 2 plus square root of 2, 2 minus square root of 2. There's a 2 in front of that, or 1.5 in front of that. I almost forgot. And we'll put that in here, and then basically everything right here was able to come out of here, so we just have a minus 1. And that's the difference. I guess we could, you can massage it a little bit differently there, but in its most raw sense, essentially, that is the answer that we were looking for, is this value here. So it is constant, which is exactly what we're looking for. Makes sense after doing the integration, but analyzing this, it's not anything like really physically enlightening, other than the fact that we were able to exercise a lot of the not dimension analysis, but a lot of tricky ways to utilize triangles and known values in order for us to kind of exercise our knowledge of these 3 variables right here in attacking this problem.